Today we're going to start chapter 6, Wind Power Systems. In this chapter, we have 12 sections. Section 1 talks about historical development of wind power. Section 2, types of wind turbines. Section 3, power in the wind. Section 4, impact of tower height. Section 5, maximum rotor efficiency. Section 6, wind turbine generators. In this section, we will focus on the first two, section 1 and 2. Section 7, speed control for maximum power. Section 8, average power in the wind. Section 9, simple estimate of wind turbine energy. Section 10, specific wind turbine performance calculations. Section 11, wind turbine economics. Section 12, environmental impact of wind turbines. In this lecture, we'll first talk about Section 6.1, historical development of wind power. Wind has been utilized as a source of power for thousands of years. It can be used as a propelling sailing ships, grinding grain, pumping water, and powering factory machinery. Figure 6.1 shows the worldwide installed wind power capacity since from 1995 to year 2003, and the data is from AWEA, American Wind Energy Association. It can be seen that the net annual addition to capacity has grown by over 25% per year since mid-1990s. Globally, the countries with the most installed wind capacity are shown in the figure 6.2. As we can see that Germany has the largest number of wind capacity, and followed by Germany is Spain, and then United States, Denmark, and India. In the United States, the California continue to have the most installed capacity. But this data is in the year 2002. At present, China is the largest wind power capacity country. Figure 6.3 shows the installed wind capacity in the United States. The California has the highest installed capacity among the other states. Texas is rapidly closing the gap. They have installed a large number of turbines along the Columbia River Gorge in the Pacific Northwest, and the windy Great Plains states are experiencing major growth as well, such as Minnesota, Iowa, and Oregon. Section 6.2, types of wind turbines. These slides provide you a number of technical terms to talk about wind generator. The wind generator also sometimes can called wind energy conversion system or wind turbine. One way to classify wind turbines is in terms of the axis around which turbine blade rotate. Most of are horizontal axis wind turbines called HAWT, but there are some blades with a spring around the vertical axis called VAWT. Figure 6.4 shows the horizontal axis wind turbines and the vertical axis wind turbines. Graph A shows the upwind horizontal wind turbines, while graph B shows downwind horizontal wind turbines. As we can see, the horizontal axis wind turbines include the tower, nacelle. In the nacelle contain the generator, and here is a gearbox. This is called a rotor blade. And upwind HAWT face the wind. Downwind HAWT, the wind is blown over the back of the turbine. Behind the blade. The direction and the turbine is different. The vertically axis wind turbine is also called a Darius wind turbine. Vertical axis wind turbine accept the wind from any direction. The structure of vertically axis wind turbine contain the gearbox actually at the bottom, and this is called the rotor blades, and on top is a gate wire, and the wind can be blown from any direction. For vertically axis wind turbine, the advantage include they do not need any kind of yaw control to keep them facing into the wind. And the heavy machinery contained in the cell, and the cell is located down on the ground, so it can be served easily. The cell contains the housing. The cell is the housing around the generator, including gearbox and other mechanical components. The disadvantage of vertically axis wind turbine is that the blades are relatively close to the ground, where wind speeds are lower. In low speed wind, Darius rotor have very little starting torque. In higher wind, when output power must be controlled to protect the generator, it cannot be made to spill the wind as easily as a pitching controlled blade on a horizontal axis wind turbine. So almost all of the wind blades are of the horizontal axis type. But there are still controversy over whether an upwind machine or a downwind machine is the best. A downwind HAWT has the advantage of letting the wind itself control the yaw, so it naturally orients itself correctly with respect to wind direction. But they do have a problem. The problem is the wind shuttling effect on the tower. Every time a blade swings behind the tower, it encounters a brief period of reduced wind, which causes the blade to flex. This flexing not only has the potential to lead the blade failure due to fatigue, it also increases the blade's noise and reduces power output. The upwind horizontal X wind turbine requires complex yield control system to keep the blade facing into the wind. In exchange for that added complexity, upwind HAWT operates more smoothly and delivers more power. Most modern wind turbines use the upwind type. Another fundamental design decision for the wind turbine relates to the number of rotating blades. Wind turbines with many blades operate with a much lower rotating speed than those with fewer blades. So as the RPM rotation per minute of the turbine increase, the turbulence caused by one blade affects the efficiency of the blade that follows. With fewer blades, the turbine can spin faster before this interference becomes excessive. And a faster spinning shaft means that the generator can be physically smaller in size. Now we complete this section 6.1 and 6.2.